The title of this presentation is Discrete Probability in Quantum Information Theory, Error Correction, Integrability, and Future Prospects. To begin with a presentation overview, I wanted to discuss a couple preliminaries which are relating to a presentation, a conference presentation that I gave in Las Vegas around a couple of years ago in 2021. And this is really going to be describing and providing some information on more of the discrete probabilistic side of things, from which I'll establish several comparisons with error corrections, integrability, and exact solvability, and now how that relates to several works that I've been pursuing in between statistical physics and quantum physics. And in this discrete probabilistic setting, what's really helpful to first consider is that a lot of these arguments from probability theory describe classical Russo-Simmer-Walsh or RSW arguments that have historically been applied to Bernoulli percolation. Bernoulli percolation is a stochastic process that's given by independently tossing a coin, and depending upon the flip of a coin, namely whether you encounter a heads or a tails, over the square lattice Z2, you either occupy edges independently at random with probability either p or 1 minus p respectively for some strictly positive parameter p. In Kessin, in his seminal work in 1982, he demonstrated that the critical point of PC of Z2 is equal to a half, which is pretty remarkable because actually in a lot of models in statistical physics and even in other areas of quantum physics where you're trying to anticipate or expect or study qualitatively different behaviors of a phase diagram, they don't have this nice, very simple closed form value such as a half, which is really why it's so remarkable that Keston was able to make all of these conclusions and all of these observations about, say, the incipient infinite cluster and several other types of related objects for Bernoulli percolation. However, for different types of models, which can be defined on other types of lattices, or maybe that don't have as nice of a closed form explicit representation for the critical point and the critical value as Bernoulli percolation does, relating to the second point in this preliminary slides, it is of related research interest to determine whether RSW results or these crossing probability estimates can still be obtained for other models in statistical mechanics, statistical physics that are not self-dual, because this is relating to the fact that the Ising model, which is another model, another very classical model of statistical physics that many people study, like how they study Bernoulli percolation, has many connections with percolation, and it's one classical model which is dual to itself at the critical temperature. So just like how I mentioned that Bernoulli percolation is very nice because from Keston's seminal work in 1982, he had derived a 1/2 value for the critical exponent, or sorry, for the critical value for Bernoulli percolation. There's a critical temperature, and in fact, a line of critical temperatures, which is establishing several connections and several properties of, say, the Ising model, as well as connections with the Ashkin-Teller model, which is basically coupling two Potts models together. And our prize, more formally speaking, is that we want to describe a Russo-Simmer-Walsh or RSW result, given by the fact that we're looking at phi, well, which I haven't defined it explicitly, but it's just the probability measure for the random cluster model, which is very closely and intimately related to the probability measure for Bernoulli percolation, because on the random cluster model, we're allowing there to be positive probability that there can exist some clusters, which is given by a parameter q to the number of connected components. However, the remaining terms in the probability measure for the random cluster model is given as the same exact terms as what's appearing for Bernoulli percolation, namely the number of edges that are open p times 1 minus p times raised to the number of edges that are closed. And this probability measure is used to construct a Russo-Simmer-Walsh or RSW result because this result is an inequality of the following form. Namely, we're looking at, like we're saying, the support of the random cluster measure that's given in the first item. Namely, we're fixing some strictly positive parameter rho, and we're looking at a box of aspect dimension minus n by rho plus 1 of n by minus n to 2n, in addition to the fact that the image or the event that we're pushing forward under the random cluster probability measure is given by a horizontal crossing event, namely a horizontal crossing event script H, where the support is given by 0 by rho n times 0 by n. And third, it's also very important when we're talking about Russo-Seymour-Welsh, and even like I'll describe in more of the quantum side for quantum information processing and quantum information theory, the boundary conditions that you enforce on a system. And in particular, from discrete probability, boundary conditions are defined over finite volume. And it's actually very important to determine what would be the boundary conditions for this instance for the random cluster model through this random cluster probability measure that would be the most conducive to maintaining long horizontal crossings across appropriately defined scales, like how we've been introducing with this rho quantity here. And this is to say that this probability of this horizontal crossing event is bounded by below by C of rho and above by 1 minus C of rho. So this is to say that these crossing probabilities do not degenerate, and they don't trivialize to either 0 or 1, which is why this boundary condition is very important. In the random cluster measure, it satisfies several interesting properties that were originally introduced in a lot of works by Dumenil, Copin, and Tassion from this reference that I talked about in that conference in Las Vegas a couple of years ago, and how it relates to the following three properties, namely FKG, four twin Castellan, Ginibre, lattice condition. Sorry, I think I pronounced that correctly. The spatial Markov property SMP, and a comparison between boundary conditions CBC. For the first property, for the FKG inequality, if we fix A and B to be two increasing events, which is meaning that the probability of A and B increases monotonically with respect to the number of edges that we add to the configuration or to the event, or into configurations that are supported over the random cluster measure, the random cluster measure of phi under the same boundary condition C of script A and script B occurring is bounded below less or is greater than or equal to the product of the two respective probabilities for A and B. The spatial Markov property dictates that the random cluster measure, conditionally upon the fact that we're looking at the random cluster measure with boundary condition C with support G, is given by this conditional probability conditionally upon the fact that omega E is equal to CE for all edges between E and F is instead equal to another random cluster probability measure, just given the difference that we're appending the boundary condition C prime, as well as increasing or enlarging the support of the random cluster probability measure to be over H instead of over G, which is given by the support of the conditional probability measure for the random cluster model. And finally, the last property with the CBC, comparison between boundary conditions, is saying that if we have C, which is dominated by some other boundary conditions, the probability under the larger boundary conditions stochastically dominates the probability of the random cluster model under boundary condition C. And there's a special case of the CBC property with a maximum of k new clusters wired on the boundary of finite volume that Dumenil, Copin, and Tassion make use of in their work that I had cited in my first preprint on the archive for renormalization of crossing probabilities in the dilute Potts model. And what they say is that you can have a special case of this last property of the random cluster probability measure because you're looking at Q to the minus maximum number of clusters under one boundary conditions minus the possible number of clusters that you can count under another boundary conditions minus the minimum of the difference of these two boundary conditions, which is being multiplied by which serves as a prefactor, this Q to the maximum minus minimum number of clusters to the probability measure under the larger larger boundary conditions that we use to form the stochastic domination for the CBC property of the random cluster measure. And now I wanted to describe a little bit informally just how one would look to make use of a lot of these types of properties with the dilute Potts model. And the dilute Potts model is another type of model that Dumino, Copan, and Tassion mentioned would be really interesting to determine what would be the currency or applicability of the renormalization of crossing probabilities arguments. And I'm going to be describing some discrete probabilistic aspects of the interfaces that one would look at when you're trying to form arguments for renormalization of crossing probabilities, and kind of slowly hint at and describe after a couple of slides how these types of observations in discrete probability could be used to describe topological aspects of error correction and other aspects of quantum information theory that could be of interest to further study and examine. And this is given by the fact that we're going to be introducing a few similar, oh, sorry, the FKG inequality got cut off at the bottom of the slide, basically there are very similar types of properties that can be introduced for the dilute Potts model as they were for the random cluster model, namely the SMP, namely the spin spatial Markov property, relating to the fact that one can introduce the dilute Potts model as a high temperature spin expansion of the loop ON model, in addition to the fact that there's spin CBC, spin comparison between boundary condition properties, and as well as the FKG inequality, which it just takes the exact form as that which was provided for the random cluster model in the previous slide, only the fact that there's just a difference in probability measures. And this is to say that for the first property, the spin spatial Markov property, we can visualize two hexagons embedded within each other, an inner domain and an outer domain, respectively. And it's helpful to look at hexagonal boxes or hexagonal finite bums because that's the ambient lattice that the dilute Potts model is defined over. And we can imagine that we would want to quantify the crossing probabilities from any one of these sides, 1, 2, 3, 4, 5, 6 of the innermost domain, of the inner domain of the smaller hexagon, to the outer domain, which can be given by the fact that we're stretching or applying some dilation factor from the inner domain to include the outer domain. And probabilistically speaking, this is given by the fact that we can have a comparison between boundary conditions, which has a very similar form to what was given in the previous slide, where we're talking about this Q to the maximum minus minimum number of clusters. But just now we're looking at an exponential for the dilute Potts model and this high temperature expansion of the loop ON model. We're looking for an exponential of these two terms, namely one term which is accounting for, as I've indicated in this figure, the impact of monochromatically colored triangles, namely triangles which are given over the hexagonal lattice, where each one of the vertices over the dual triangular lattice to the hexagonal lattice is colored black, in addition to other contributions from another external field H. So H and H prime are taken to be strictly positive parameters, and these R of T prime and these R of tau prime and R of tau and these terms which are appearing in each one of these powers of the exponents, they're quantifying what would be the expected difference in the number of monochromatically colored triangles and how this is coming into play from the high temperature expansion from this exponential factor to the loop ON model. Furthermore, we're looking at a difference in the number of edges as well as a difference in the number of connected components, which are other typical parameters which come into play for people looking at lattice models in statistical physics. And what we're looking at is that if A prime is some event of interest, we're looking at mu of tau, which is supported over the hexagonal lattice, as being upper bounded by mu of tau prime, which also has a support over the hexagonal lattice of the same event occurring. So this is just a different type of manifestation of the spatial Markov property for the high temperature expansion through the spin measure, which is given by visually embedding an inner domain and an outer domain over the hexagonal lattice into each other, and then determining what would actually be the difference or the impact for monochromatically colored triangles as well as the two external fields. Also, relatedly, the spin comparison between boundary conditions is given by also embedding an inner domain and an outer domain, But we're changing the configuration of these domains within each other a little bit because instead of actually strictly containing or strictly embedding one inner domain within an outer domain, which is given by the SMP property, we're looking at actually laying over parts of the edges which are given in this side of the hexagon. And then we're actually determining the comparison between boundary conditions as the difference in the edges from the inner domain and the outer domain, which is to say that we're looking at mu of tau of some event A occurring some increasing event A, which is stochastically dominated by mu of tau prime of the same event A occurring, where again, to be a little bit more explicit, the parameters which are given in the support of this probability measure are little n, the number of loops, x is the position over the hexagonal lattice that we're looking at the loop over, as well as h and h prime, which are the two external fields. In the dilute Potts model, it has a rich quadrichotomy, namely a range of four possible behaviors, which is very interesting, and it's relating to several different types of possible behaviors that can occur in quantum information theory, and specifically when you're trying to perform error corrections in several related types of topics. And this is given by the fact that theorem in a preprint on the archive that I'm probably going to be making some further edits to soon. We're looking at theorem 2 star in my project, which is describing an adaptation of hexagonal crossing probabilities in the quadrichotomy from the result that I've been citing and discussing for the random cluster model, which is to say that in the dilute regime of the dilute Potts model, this high temperature expansion of the Lupo-N model, which is given by restricting x to be less than or equal to 1 over square root of n, namely 1 over the square root of the number of loops, where the number of loops is strictly restrained to be between 0 and 2, non-inclusive. We're looking at an aspect ratio little n of a regular hexagon, which is embedded in some finite volume over the hexagonal lattice script t and some strictly positive c, as well as a crossing event script h across this finite volume across the hexagonal lattice. The estimates on the crossing probabilities with free, wired, or mixed boundary conditions satisfy the following criteria in the following four possible behaviors. Namely, we have four phases of interest: subcritical, supercritical, continuous critical, or discontinuous critical, where subcritical is describing the fact that the probability of obtaining a horizontal crossing event across this finite volume H is given as decaying exponentially fast, namely exponential minus Cn for the subcritical phase as the first phase of interest. The supercritical phase is given by the fact that for every n greater than or equal to 1, under free boundary conditions, the probability of the horizontal crossing event occurring under the dilute Potts model is greater than or equal to 1 minus the same exponential which occurred in the first item, as well as continuous critical, which is relating to the Russell-Seymour-Welch property that I described earlier, which is to say that for, again, the same choice of n greater than or equal to 1, independently of boundary conditions tau, the horizontal crossing probability of the dilute Potts model is between C and 1 minus C, so it doesn't degenerate, as well as discontinuous critical, the last property of interest, which is saying that the dilute Potts model under wire boundary conditions of this horizontal crossing event occurring is greater than or equal to 1 minus exponential of Cn for free boundary conditions, while under open boundary conditions, the horizontal crossing probability decays exponentially fast. And it's really helpful to visualize a lot of symmetric domains because actually a lot of these topological properties come into play for error correcting codes and other types of related information processing tasks that I'll be describing a little bit later soon. And this is to say that we're interested in looking at a lot of these symmetric domains because they have a lot of symmetry and they can be a little bit pathological because they can have many types of crossings as well as determining the numbers of crossings and actually the points along each boundary that they intersect, which can be used to construct symmetric domains. And our objective is that we basically want to ensure that under a vanishing mesh size, that we would actually be able to have some type of beneficial trade-off in terms of horizontal crossing probabilities from that quadrichotomy of four possible behaviors that I provided in the previous slide. And we can even see that in this case, we have one path that can have loops and cross itself a couple of times or even several times, depending upon the parameter of n that you little n that you take. But we really want to restrict ourselves to maybe a few loops or maybe one loop at most. And how, in fact, how these loops and these configurations that we can sample over the hexagonal lattice that are supported by the high temperature expansion of the loop ON model through the dilute Potts model, it's actually relating to these demarcated points, which I've indicated in bold, x sub 1, x sub 2, x sub 3, and x sub 4, as well as x sub I, that are relating to the points that we're using to construct the left and right sides of these symmetric domains across which there's good horizontal crossing probabilities. So now that I've described quite a few of the discrete probabilistic aspect and the discrete probabilistic side of things, I wanted to go to another application of statistical mechanics from some other work that I did in a synthetic biology lab and how this is actually relating to other types of ways that we can make use of this type of thermodynamic perspective. And this is to say that we're looking at a differential equation for analytical solutions I constructed for first passage times. Passage times are actually even of great interest in percolation themselves because they relate to Boozman functions and several other types of arguments that many people look at and even being able to quantify properties of KPZ universality. But in this case, for more of a synthetic biology perspective, they're relating to a Fokker-Planck equation, or it's pretty much relating to a type of generalized reaction equation. And it's relating to the fact that we want to be able to quantify or generate some exit or passage time distribution tau of x, where x is maybe relating to some spatial position along the genome that, say, a CRISPR-Cas nuclease or other types of enzymes can target for genetic editing, and how this would relate to simulations of protein inspection processes, which is relating to either diffusion along either a DNA or RNA template strand to determine which types of targets would be most favorable for some type of enzyme to target, or whether it's catalytically inactive or catalytically active, and how that would actually relate to different types of properties that we would hope to gather. And this is given by the fact that this protein inspection process is given by a second order differential equation with a non-constant coefficient, namely a u prime of x term, where this landscape term is where this second term, which is appearing in the non-constant coefficient to the first derivative of the passage time distribution, is given as u prime of x, subject to the conditions that at tau of n, the passage time will be 0 because the protein will have diffused up to some position n, little n, as well as given by the fact that at the beginning of the diffusion process or this protein inspection process, tau prime of 0 is equal to 0 for n being some integer, because we want to inspect an integer number of positions along the genome for maybe genetic editing or other types of purposes for biotechnology. And it was really helpful to look at different types of explicit solutions or closed form representations for tau of x, namely the passage time distribution, which I analytically derived as being as 1 over the reciprocal of the Boltzmann constant times the temperature times three contributions or three terms: an absorbing boundary condition, an exploration position term, as well as an error function double integral where the function f of hi of v and f of hi of u that I given here is given as an exponential of this error function. So just basically an integral of exponential of minus t squared of dt. And we can fashion additional analytical relations from this explicit closed form representation of the solution that I gave, which is just relating to the fact that maybe we would be interested in maximizing the first passage time given a landscape barrier height and some binding temperature, which is again relating to some of the parameters which I described and made motivated from the perspective of statistical physics and crossing probabilities and Russell Seymour Welsh from the loop ON model because it's depending upon some type of temperature parameter, which is coming into play through the high temperature expansion and through these two external fields that I defined for the viewer and motivated through those H and H prime parameters. But in this case, we can look at a time dependence of the temperature, as well as looking at other types of functions which are related to that error function, which are appearing in this analytical expression from the previous slide, and how that actually can help us determine whether there's some trade-off in terms of the energetic cost and the landscape barrier height, as well as the temperature. And furthermore, we can also look at first passage time fluctuations, which are even relating to a lot of types of fluctuations that people look at in statistical physics, and it's of interest for them to explore because they're basically looking at, like how I was trying to quantify here, how would the how would the first passage time expect to change or to deviate depending upon the temperature and the landscape barrier height? And obviously, we're getting contributions to this passage time fluctuation for this enzyme or for the protein inspection process in terms of an error function double integral, which is relating again to the exponential, the error function, which was given in the analytical solution that I gave in the previous slide, as well as absorbing boundary condition terms and exploration terms. So it's really a pretty robust type of expression, allowing for either varying the total number of base pairs along the genome or along some template strand, like I mentioned, that a protein or an enzyme can examine, as well as these error function double integral terms. And I've really came into this perspective in this presentation and trying to describe and motivate several works in statistical physics that I've undergone, whether it be relating to the random field Potts model or looking at constructing incipient infinite clusters, or just basically various types of crossing probability estimates, whether it be relating for the Gaussian free field or the six vertex model. And pretty much this is actually all together, or even to the quantum inverse scattering method for Poisson structure and integrability of a Hamiltonian flow for the inhomogeneous six vertex model. And basically, all these types of perspectives together, they're very helpful in terms of trying to determine whether there be anything of interest on the quantum side of things, which I'm going to transition more to now. And this is to say that there are a couple of previous works in quantum physics that I've had in that, I pretty much pursued in the past that have really benefited from some of my background in discrete probability that I've been discussing and motivating for the viewer. In the first one of these presentations, and that I've given a few presentations with for at the APS March and April meetings, as well as some other seminars, is relating to variational quantum algorithms. But then I looked into more of the theoretical side of things for two-player games, two-player game theoretics situations relating to XOR star and FFL games, as well as more recently this year in 2025, looking at quantum multiplayer game theoretic situations, as well as relating it to converse upper bounds on the bit transmission rate through error correction, authentication, and false acceptance probabilities. And I wanted to first describe a couple of these aspects of the quantum information side of things and how that's actually helpful for us here. Namely, the fact that we're looking at an SDP or a semi-definite program formulation, which is very helpful for being able to characterize different types of aspects of optimality and actually different phases of behavior in quantum information theory, which is very much relating to those types of aspects that I described in terms of, say, a quadrichotomy of four statistically indistinct behaviors and how that can actually be related to computational complexity, in this case of quantum information processing tasks. And this is to say that we're looking at a semi-definite program formulation because it comes into play in terms of G and Z, because Z is the primal feasible solution for the semi-definite program, and G is the game matrix, as well as a supremum, which is taken in terms of with respect to a partial ordering of the positive semi-definite comb, given the fact that we want this Z quantity, which is a primal feasible solution of the semi-definite program, to be strictly greater than or equal to zero with respect to this ordering of the partial semi-definite comb. And we want to enforce the condition that another constraint F, which is relating to a duality constraint that I'll introduce soon, multiplied with the primal feasible solution is identically equal to C sub I for all I between 1 and little m. And in a way that I describe duality, there are several types of forms of duality amongst various areas of physics. And for one, it's really interesting to think about how basically you can formulate a dual semi-definite program just basically by interchanging the constraints that was given in the previous slide, as well as switching a supremum to an infimum, and how still we're looking to enforce some ordering with respect to the positive semi-definite cone, which is again relating to this larger auxiliary space over which we're performing this semi-definite program optimization. And we can also look to formulate a duality gap SDP formulation because when we're talking about quantum information processing tasks and actually determining whether there's some reputable or whether there's some verifiable, as many companies like Google put it, quantum advantage, we're looking at a difference between, say, a duality gap SDP formulation, which is to say that we're looking at whether there would be some dual constraints F sub I and Y sub I, which so that when we take the summation over little m of these terms and we subtract from the game matrix and multiply by the primal feasible solution, whether that would be greater than or equal to zero. Or maybe even a more strong condition would be whether this summation in this term that's being multiplied by the primal feasible solution of the semi-definite program is strictly positive. In multiplayer game theoretic settings, like I've been describing for the viewer, it's come up in more of this preprint of the archive that's currently submitted, and it was the first version that I put on was in May of this year, and pretty much I was looking to start from the bias of a two-player game because the bias beta is given as the expression of being related to a game G as well as the set of all possible strategies script S, which is given by a summation over little s and little t, where these little s and little t terms are respectively belonging to big S and big T, namely the set of all possible questions that can be distributed to the two participants, Alice and Bob, that are drawn from the referee's probability distribution. And the summation is being given over a game matrix G of S of T, as well as a bracket state where psi is denoting the optimal value. So presumably, this optimal value, psi, is what Alice and Bob would want to use so that they can harness the maximum quantum advantage in their games. In the middle term, which is appearing in this bra and kept psi term, is given by A of S tensor B of T. So namely, the tensor of observables that Alice can construct from the questions that she receives from the referee's probability distribution, as well as the tensor corresponding to Bob's possible responses to the questions little t that are drawn uniformly at random from the referee's probability distribution. And multiplayer game theoretic tensors are also important because it's relating to the fact that if we want to add on an additional layer of complexity or an additional participant to this game, we can say Cleo is also another player who wants to participate in the game with Alice and Bob. We can add a tensor product of her observables, Cleo's observables, onto the space of all of the tensor product of all player tensor observables, which would admit identically the decomposition in terms of Alice's observables, Bob's observables, and Cleo's observables. And the multiplayer bias is given by the fact that if we fix some strictly positive parameter epsilon, the multiplayer bias will satisfy an approximality condition, which is given by the fact that the bias is lower bounded by a 1 minus epsilon multiplicative factor, and it can be less than or equal to a summation over a number of questions over the bra of an optimal strategy of a game with a tensor product of the tensor of player observables over the however many number of players there are in the game, as well as being multiplied by a ket of an optimal strategy for the multiplayer game, which is less than or equal to the bias of the game. But rather than the multiplayer game theoretic situation, which has some straightforward connections with the two-player game theoretic situation or game theoretic scenarios, we can look at parallel repetition of semi-definite programs. And this is relating to the fact that a lot of people in the quantum information processing literature, they're very interested in being able to conduct experiments, so to speak, or actually being able to run out several information processing tasks repeatedly or in parallel. And it's kind of related to a lot of information or a lot of arguments that are talked about in more of the statistics side of things from independent Bernoulli trials, which is just basically relating to the fact that, again, you may want to perform some type of constraint optimization procedure like I've given on the slide repeatedly. So this is to say that we're looking at G, which is some parallel repetition of the game matrix, which is being multiplied by some primal feasible solution, as well as given by the fact that the constraints that we're looking at for the supremum for this for parallel repetition of the semi-definite program is given by some parallel repetition of the primal feasible solution, which is taken again with respect to the partial ordering of the positive semi-definite comb, as well as just being between i's between 1 and little m, as well as, again, given the constraint, which is similar to the original semi-definite program formulation, we're taking some type of constraint f and multiplying it by the parallel repetition of the primal feasible solution, which is identically equal to C of j sub I. And equivalently, parallel repetition of semi-definite programs can be formulated with primal feasible solutions and game matrices of settings before the parallel repetition operation is obtained, which is to say that we can just apply this parallel repetition operation and just take the supremum, namely the semi-definite program, this constraint optimization problem, over just the game matrix times the primal feasible solution for the XOR game. And alternatively, along the lines of comments that we've been describing, it's really helpful to look at parallel repetition of question sets, because parallel repetition of the question sets that are distributed to each player, Alice and Bob, or however many number of players in these multiplayer game theoretic settings that we've been describing, is of interest. Which is to say that script q sub I raised to the tensor product of little k can be given by identically being equal to the set of all questions, where we're having a collection of tuples where in each one of the tuples we have k terms or k questions, but we're repeating this indefinitely corresponding to each one of the pairs of questions that we would distribute to Alice and Bob during each round or each instance of parallel repetition. In parallel repetition of the XOR optimal value and the FFL optimal value is different because these games have different types of probabilities that are interested or that are introduced just basically for the assignments of different responses from Alice and Bob in the game. But under 2 rounds of parallel repetition, the XOR game and the FFL game, they differ because the XOR game, namely XOR wedge XOR of the 2 parallel repetition of the XOR game, is given by a product of the optimal values, namely the maximum winning probabilities for Alice and Bob, which is to say that it can be identically decomposed as just the product between 1 and 2 of just the optimal value of an XOR game without performing parallel repetition raised to the j power, which is identically being equal to a half, which notably and importantly is not equal to 1 over square root of 2, which is the original value for the original maximum winning probability of the XOR game before parallel repetition is performed. An invariance of parallel repetition for the optimal value of the FFL game is given by the fact that instead we can look at omega of FFL wedge FFL, which is given by the fact that this is actually equal to the FFL value, which is equal to 2/3, which in comparison to the optimal value that was given in the previous slide, it's not equal to the square of 2/3. And in another work from this year that I've been describing, it's also a related result like I described to formulate complexity theoretic related results, which again is kind of relating to those different types of quadrichotomy or those 4 possible ranges of behavior in the dilute pos model or other models of statistical physics, but with more of a quantum aspect or a quantum interpretation to it, because it's describing how maybe there could be some type of algorithm or quantum algorithm which could offer some type of maybe polynomial time speedup to some type of classical algorithm that would then allow us to uncover or unveil some novel types of applications that we could theoretically and also algorithmically explore. And in this case, I just wanted to provide the attention of the viewer to a couple of just very briefly some results that I'd given from a paper that I'd extended the results of and interpreted from Bavarian, Vidic, and Ewan. It was a really interesting work that these authors provided because they pretty much described how to just basically either like I provided in the statements here, theorem one, theorem two, and theorem three, just basically quantifying the largest order of a system of expected values and how this relates to also given in theorems 2 and theorem 3, quantifying the largest order of a positive operator valued measurement system, and also making use of Pinsker's inequality in theorem 3, which is just basically relating the L1 norm to the fidelity. So this is really important because these types of complexity theoretic related results, they're ultimately relying on probability. Even though maybe it's not exactly the same way in terms of defining a model over a lattice and introducing a normalizing constant through a partition function, what it's actually really relating to is that we're looking at, say, as was given in this first result in theorem one, being able to look at some big O notation, which is very standard complexity theoretic related notation of some delta and some alpha parameters, which are just basically parameters that you can introduce in this system of expected values, which is basically taken with respect to some probability measure, because that's how we define an expectation. You first define a probability measure, and then you can define expected values of observables or other types of quantities of interest with respect to this base probability measure. But in theorem two, a generalization of this probability measure comes into mind with the POVMs because POVMs, positive operator value measurements, they sum to the identity, which is given by the fact that you're just having an identity matrix and you're having ones along each one of the diagonals. So the ones, each one of those ones along the diagonal is corresponding to literally, directly a probability of obtaining or sampling some type of system in some fixed configuration with a value 1. And it's demonstrating how besides the configurations which one could construct some from finite dimensional representations, all of the other entries of this POVM that are summing to the identity outside of the diagonal are 0, and how that's relating to some complexity related theoretic result because we're having that this largest order of the POVM system of expected values is being bounded by some big O notation. And finally, in theorem 3, we have some type of related result. And so the overview is that so far we've been further building upon discussions of quantum games in the previous presentation, or the previous part of this presentation, including the set of dependency breaking variables, demonstrating how entropy, the relative min entropy, can come into play, as well as just drawing the attention of the viewer to the fact that parallel repetition can also interact with anchoring, which is a form of dependency breaking. And this is helpful because we're further discussing how computations with the entropy determine upper bounds for the POVM system, the positive operator value measurement system, and related arguments for multiplayer game theoretic situations, and how this POVM system is really relating a lot to probabilities that I introduced in more of a discrete sense at the beginning of the presentation. And this is to say that the anchoring and probabilities is coming into play because we're looking at the probability of sampling some question A sub I and B sub I for Alice and Bob, conditionally upon the fact that little x and little I and little y are distributed to Alice and Bob uniformly at random from the referee's probability distribution, conditionally upon the fact that they're winning the game across all coordinates. And this is to say that the anchoring condition, which again is related to some conditions and observations provided by Bavarian, Vidic, and Ewan, is given by the fact that this probability is approximately given by the probability of setting one of the questions x sub I to an anchored value, as well as also being approximately related to the probability that the second question and the first question simultaneously are set to this anchored value. And the statistical condition is relating to the fact that we can look at, with respect to the absolute value norm of the probability of A sub I and B sub I, conditionally without anchoring minus the probability of anchoring in one question being approximately roughly the same or approximately zero, as well as in the second condition with respect to the standard little absolute value norm, the fact that we can also look at just the probability that the first that Alice and Bob can sample some questions or provide some answers in response to the questions drawn uniformly at random from the referee's probability distribution, given the fact that the first question is anchored, and comparing this to whether both of the questions that are initially distributed to Alice and Bob are anchored. And the multiplayer dependency breaking variables are relating to the fact that if we want to look to remove some types of correlations or introduce some type of dependency breaking, which is very much related to concepts that are introduced in statistical physics, we can look at this set of dependency breaking variables as omega multiplayer, which is given by identically being related to a union over little omega, which are belonging to the multiplayer dependency breaking set, which is given by the fact that this omega term is a dependency breaking variable for position j. So we pretty much want to vary the position amongst all of the coordinates or all the instances of parallel repetition and determine what type of dependency breaking situations we would encounter. And the space of all strategies is given by script m, which is given by identically being equal to script sub n, or the calligraphic n, which is belonging in script sub n, which is given in terms of a union over all strategies, where the probability that the players can win using the strategy intersected with the probability that the strategy satisfies these two properties simultaneously is strictly positive. And these two properties, usefulness and sampleability, they're pretty much relating to the fact that you want to be able to determine whether obviously some type of strategy or some type of course of action is useful, as well as sampleability, namely relating to the fact that whether someone could actually be able to sample some type of just basically configuration or some type of strategy from this larger auxiliary space of strategies for which they could win this game with strictly positive probability. And the set of product strategies is given by the fact that it's relating to the parallel repetition of these strategies, namely script sub n is given by identically being equal to the parallel repetition between 1 and j and little n of just script of j, which can identically be expressed in terms of a product over these script sub j terms, which is equal to the product between 1 and j and little n of just basically strategies of ket up psi sub j, where each one of the players can participate in the game using this ket psi sub j term. And the Bell states and the EPR pairs, they're very much related to the fact that this is the middle, this is the model system for entanglement, because when we're looking at and talking about entanglement, this is the simplest type of system that one could actually look to be able to have in terms of being able to quantify just what would be the expected impact on correlations in entanglement. And it's just given by the fact that you can look at either the identity operators or the poly Z or the poly X sigma operations and just basically taking a tensor product, either the identity tensor product with itself, sigma X tensor product with identity, sigma Z tensor product with identity, sigma X, sigma Z tensor product with identity, and just basically looking at what would be the expected result of this tensor product of two operators from either on the 0, 0 plus 1, 1 states normalized by square root of 2. And so just basically the probabilities of sampling the multiplayer dependency breaking set is relating to the fact that this big omega term, conditionally upon the fact that each one of the questions that's distributed to the players that's identically equal to x, subject that the players win across all coordinates, can equivalently be expressed through a chain of probabilities, and pretty much you're removing off and cleaving off each one of the questions for each one of the players at a time and setting them equal to different values. And this is then allowing us to establish a comparison, like I had mentioned previously early in the presentation, in terms of that little L1 norm absolute value, standard absolute value statistical condition in which you just pretty much want to determine whether there would be any relation of the probability of Alice and Bob winning and how that relates to anchoring or setting their questions to some value, which is in effect introducing some type of dependency breaking mechanism, removing correlations from the system. And this set, boldface X, which is appearing in the conditioning for these probabilities, is given by the fact that it's relating to the responses from each one of the players that are drawn uniformly at random from the referee's probability distribution Y or pi, which is being identically equal to the union over all the number of players. And the anchoring probability corresponding to each player is defined as follows. Just basically, the probability for the question supported over the question set is equal to just basically the answer that's given equal to the anchoring probability, which can be equivalently expressed as just the probability with respect to the question set that player one responds to a question from the anchored set, which is equal to alpha. And we're just basically setting the probabilities for each one of these players equal to each other. And the computations for upper bounding the POVM system, which, like I mentioned, it's this generalization of discrete probabilities, is related to the relative and relative min entropies, which is just to say that we're looking at some expectation value, which again is taken with respect to some base probability measure. And we're looking at, say, the relative min entropy of state one and state two, which is just given throughout the literature of quantum information theory, S sub infinity of state one with state two. And the relative min entropy is defined in terms of just the minimum over lambda such that between rho and sigma, these two quantum states, such that rho is less than or equal to 2 to the lambda times sigma. In the rate of decay of the optimal value of the two-player game under parallel repetition, it has this form. I'm kind of running a bit on time, so I just wanted to maybe skip this slide, but it's just basically relating to the fact that you can have some type of expression for parallel repetition under k rounds. And there are suitable unitaries that we have to introduce for each player, namely u sub 1 up to u sub m, which are corresponding to the unitaries which we introduce for the usefulness and the samplability properties, which are relating to each one of these properties that the players are making use of when they're participating in anchored parallel repetition. And the system of expected values without normalization is given by the fact that we're looking at some type of expected value, which is helping us quantify what would be the instance of dependency breaking and symmetry breaking, which is to say that amongst all these terms, we're looking at some expectation of either, say, with respect to Q1 or Q sub 2, or even like what's given in this last expectation value over a product of expectation values. And we're looking at each one of these suitable unitaries and just basically subtracting it from the identity and looking at the norm of this as it's acting upon the optimal strategy that I had introduced first for the players in the two-player game theoretic situation. But besides these innermost expectation values, we're also looking at expectation values which are taken with respect to the dependency breaking variables, which are given by I, conditionally upon the fact that the players win across all coordinates. So we just basically want to determine whether this dependency breaking would still allow any of the players to be able to win the games across all coordinates and hence across all instances or rounds of parallel repetition. And the dependency breaking sets over the number of players can be identically decomposed in terms of a union over dependency breaking across the first k variables, the first k players, as well as just k being between 1 and big N, just namely between 1 and the number of players. And the system of expected values with normalization given by this twiddle term takes the form that was provided earlier in the presentation from 2 slides ago from other system of expected values, just given by the fact that we're normalizing the optimal value that we're computing all these expected values from. And the normalization of the quantum strategies is given by the fact that it's related to ket psi of twiddle, which is identically being equal to ket up psi normalized with ket up psi, which is proportional to ket up psi itself. And the generalized form of the system of expected values for normalized quantum strategies is related to the fact that we can further generalize this system of expected values by removing the identity operation and looking at a normalization which is appearing in all these expected values. So this is to say that just pretty much all these expected values and these types of probabilistic computations I've been describing and motivating for the viewer, it's very much relating to the fact that we're trying to describe and relate this to just basically other types of forms of probabilistic computation, like I described and motivated for the viewer, but actually relating that to complexity related theoretic results and how this relates to just basically how full other types of quantum information processing tasks can be. And this table is providing an overview of some of the previous results I'd given in another work, in which I pretty much just described how one can formulate just basically from 3 XOR games up to N XOR games or multiplayer XOR games, how we can look at being able to quantify duality gaps that we described earlier in the presentation in this series, as well as primal feasible solutions, and how this relates to Theorem 1 and Theorem 6 in this other work, which are relating to strong parallel repetition of multiplayer games. So this diagrammatic representation really helps encapsulate a lot of the types of aspects that I've been describing in this presentation. And other classical and quantum games for the literature have been characterized for a wide variety of games, which are relating to just basically the torpedo game in 2 or 3 dimensions, which has different types of closed form representations corresponding to the maximum winning probability, which is either relating to 3/4 or 11/12. In the linear relation between the bias and the optimal value, it's taking the following form, namely the bias is given in terms of just being expressed in terms of the bias is 2 times the optimal value minus 1. And this relation holds for a wide variety of games, which is really helpful for actually determining, even from the simpler two-player game theoretic situation, what types of conclusions one would hope to reach. And the bias, independently of each possible strategy S, takes the following form below, namely, we want to be able to take some majorization or take some supremum over the set of all possible strategies script S, which is just given by identically being equal to beta sub G. Furthermore, the SDP formulation under strong parallel repetition, like we mentioned, it can just be expressed in terms of just looking at parallel repetition of the game matrix. So just which is to say that this parallel repetition of the XOR game can be expressed in terms of the wedge operation being applied to the XOR to parallel repetition of a finite number of parallel repetition operations applied to the XOR game, which can be expressed in terms of G wedge of I of XOR. And positive semi-definite conditions are related again to the fact that with respect to the partial ordering of the positive semi-definite cone, there are just a lot of types of ways that we can express symmetrization of the game tensor, which is given by the fact that we're constructing and embedding the game matrix into a higher dimensional space, which is identically being expressed as 1/2 of zeros along the diagonal, the tensor product of G, as well as G on the anti-diagonal. And this is expressed as 1/2 of 0, 0 along the diagonal and along the anti-diagonal, the transpose, as well as just the game matrix itself identically. And this is related to the fact that, again, we're looking at some symmetrization condition, which is relating to positive semi-definiteness, which is related to just basically for the 3 XOR game or up to the N XOR game, which is relating to these game tensors under symmetrization. And the optimal or classical optimal strategies, whether we're looking at quantum or classical, are related to the fact that we can look at just basically ket of psi of 3 XOR up to ket of psi of N XOR, which is just given in terms of a union over all players for a supremum over all strategies, as well as a player strategies S for the 3 XOR game, all the way up to the N XOR game. However, besides theoretical implications, I wanted to end out this presentation with a couple applications of noise-resilient communication protocols that can be applied for several algorithmic purposes. And this is really relating to the question about why one would want to consider quantum algorithms. And it's just relating to the fact that there are a lot of connections with variational quantum algorithms, which is a more niche type of algorithm or a specialization of the more general variational quantum eigensolver, which is relating to quantum chemistry, electronic structure computations, as well as binding affinities. And I've talked about these types of presentations across a couple of different instances on my YouTube channel, in which I was just pretty much describing the attention of the viewer, even in a remote seminar that I gave at Dartmouth, how just basically you can look at wave propagation nonlinear problems, which is relating to a lot of interest that people theoretically characterize rigorously through Sobolev spaces and various types of regularity structures. But there can also be other types of more algorithmic or computational aspects because you can look at just basically being able to approximate solutions to 15 partial differential equations in polynomial time, as well as even establishing connections with approximations to solutions of nonlinear problems that can be obtained with neural operators. So just basically using concepts from neuroscience and just basically leveraging neural networks to be able to approximate solutions to nonlinear problems of interest. And then also relatedly, how that can be related to PDE models of biological transport, which can be related to that first passage time problem and that first passage time situation in terms of that protein inspection process that I've motivated for the viewer earlier. In the previous video on implementing molecular docking simulations is particularly of interest from the quantum chemistry perspective because I'd basically described how you can make use of an open source implementation that doesn't use quantum computation, AutoDoc which makes use of classical computation, in which you have to just basically look at the distribution of pockets along the surface to say the COVID-19 receptor or other types of receptors of interest, and how that would pretty much relate to being able to formulate some type of quantum computing test to determine whether the quantum algorithm could be able to more accurately predict the chemical structure of some type of compound of interest, because after all these types of constituents of these chemicals are quantum mechanical. And in some open problems and questions that was raised by my colleague David Speck when he graduated from the School of Applied and Engineering Physics at Cornell, in the synthetic biology lab that we both worked at, he phrased several types of interesting questions in terms of what would be the unanticipated fitness effects, which are impacted from either catalytically inactive decast or dead cast nucleus or catalytically active cast nucleases, and how that just basically relates to the fact that you we encounter all these types of just basically unexpected abundance or unexpected log 10 of counts, which is just some type of experimental readout that he obtains from various assays that he designed, and how this relates to several types of aspects of just basically how difficult it can be at certain times to apply either certain types of computations for first passage time models or related types of aspects for CRISPR-Cas nucleases, and how it's actually of interest to determine how we can better inform assay development, which would help further, improve experimental readout and data acquisition. And finally, this is even related to, again, more in the theoretical sense from expansion of two-dimensional transfer matrix and large N limits from products of L operators, because this is relating to the quantum inverse scattering method that I'd alluded the attention of the viewer to, which is just basically relating to just basically distilling some product of L operators into just pretty much computations of Poisson brackets, where each one of these entries of the Poisson brackets is given by just basically block operators, which are informed by each one of these L operators. And in the instance of the 20 vertex model, which is something that was really interesting to me as a higher three-dimensional analog of the 6 vertex model, it's relating to just basically mappings into unital associative algebras and several other types of characteristics and qualities, which can be used just basically to perform these types of computations with Poisson brackets, which are underlying the integrable and exactly solvable structure, which is undoubtedly coming into play a lot in terms of quantum mechanics and error correction and the other types of information processing tasks that I've been mentioning. And this allows us to make associations between several different types of systems. So just pretty much the fact that we can start from some host genome and establish some type of structure prediction, and hopefully to establish some type of connection with quantum chemistry, and then how we would actually be able to identify potential compounds or therapeutics of interest from homology models, which are establishing some degrees of similarities from some genomic sequence. And so the conclusion is that we introduce encoding, decoding, transmission, and authentication protocols that are resilient in the presence of noise. And this is really much relating to a lot of game theoretic situations that we have been describing. And to further elaborate upon conditions under which prospective quantum advantage is expected to hold, we were describing how regular and converse results on the bit transmission rate can relate to several information processing tasks. And we were describing how just basically this bit transmission rate, which is relating to error correction itself, can help in terms of just basically several types of computations and relating to several complexity theoretic related results. And altogether, as given in the last bullet point, this is establishing rough comparisons with quantum algorithms that can be ran in polynomial time. And in future work, it remains of interest to study and further classify dynamics of quantum systems that can be mapped onto next generation quantum processors and computers, possibly with hundreds of logical qubits. And thanks for watching.